We talked about whole numbers, natural numbers, integers. Each of those are ways of talking about a specific group of numbers. Another specific group of numbers that we can talk about are the prime numbers. Prime numbers have a lot of applications throughout math, but one particular reason that we want to look at them right now is because every natural number, and we should include in here greater than 1, can be written as the product of one or more prime numbers. As a review, prime numbers are numbers that are greater than 1 that are divisible only by themselves and 1. Two is our smallest prime number. It's divisible by 2 and by 1. That's it. So it meets the definition for being a prime number. 3, similarly, is only divisible by itself and by 1. And we could continue that list with the first few prime numbers, some of the smaller prime numbers, to include 5, 7, 11, 13, and 17. Really, the list of prime numbers is infinite. We could keep going with this list, but it's generally these smaller values that we're going to need for the types of problems we're about to take a look at. In example 2, what we want to do is find the prime factorization of each of the following numbers. That is, we want to rewrite the number that we're given as the product of one or more prime numbers. In order to do that, we're going to create a tree, a factor tree, where we take our given value and split it into two numbers that multiply together to give us that starting value. For instance, in part A, we're starting off with 12. 12 is an even number, so we know it's divisible by 2. That always gives us a nice place to start. So 6 times 2 would give us 12, and that makes the first two branches of this tree. Every time we hit a prime number, we'll stop and just somehow identify that prime number, so we know that that's a stopping point and we don't need to divide any further. 6 is not prime though. It's even, meaning we can divide it by 2, so we can branch this off into 2 and 3. Now each of these branches ends with a prime number, meaning we can rewrite 12 as the product of each of those values that we ended with, the end of each of those branches. So we can write this as 2 times 2 times 3. Multiplying those three prime numbers together will give us 12. In this course, we're going to be getting into algebra, so using that x multiplication, that cross multiplication symbol starts to get a little confusing once we start mixing letters in. So instead of using that, from this point forward, we're going to use the multiplication dot to indicate multiplication. But those two statements mean exactly the same thing. We're just multiplying those values together. And since we have repeated multiplication, we have 2 times 2, we can go ahead and rewrite that as 2 squared, where that exponent means we're taking 2 times itself 2 times. So 2 squared times 3 would be our condensed prime factorization of 12. We can repeat this for any number greater than 1. So we could do this again for part B with 108, which is an even number, so again divisible by 2. Dividing 108 by 2 would give us 54. 2 is a prime number, so that would be the end of that branch that we would consider. 54 is even, so we could divide it by 2. And dividing that by 2 would give us 27. 27 is not even, but it is divisible by 3. So our two new branches would be 3 and 9. 3 is a prime number, so that branch would terminate. And then 9 is 3 times 3. So we reach the end of each of those branches, meaning that we can rewrite 108 as 2 times 2 times 3 times 3 times 3, or we can condense that repeated multiplication and write this as 2 squared times 3 to the third power, since we're multiplying by 3 times. 540 is again divisible by 2. Dividing that by 2 will give us 270. 2 is a prime number, so that branch is done. 270 is even again, so we can divide by 2, which brings an end to that branch and leaves us with 135. 135 ends in a 5, meaning it's going to be divisible by 5. And that will leave us with 27. 5 is prime, so that branch is done. And I'm going to cheat a little bit, or take advantage of the work that we did in part B. 27, we ended up breaking into 3 times 9, and then 9 is 3 times 3. So 27 is going to break into 3 times 3 times 3. Once we pick up on any patterns like that, we can always take bigger jumps, faster jumps, but we could also just break that down a step at a time if we're not comfortable with that yet. But this gives us 540 is equal to 2 squared, since we have 2 branches ending in 2, times 3 cubed times 5. We'll take a look at one last example here. In part D, we have 600. Any number that ends in 0 is also divisible by 10. So we could start off by branching this into 10 times 60. Neither of those are prime, so we have to keep dividing. 10 is divisible by 5, which would give us 5 times 2. Both of those are prime numbers, so those two branches terminate. 60 is divisible by 2, which would give us 2 times 30. And then we would have to continue breaking 30 down. We could break that into 15 times 2. And then 15 would break into 5 times 3. Looking at the ends of each of those branches, we would get 600 is equal to 2 to the third power times 3 times 5 squared.